Hello, my fellow handyman. I'm a dwarf that you might know, and welcome to the Bearded Engineer Show. Let's get started. Get yourself comfortable, get a nice cup of tea. Today we are going to talk about circuit boards. Boards everywhere, inside TVs, computers, cell phones, even inside the device you are watching me with. That's right, boards are everywhere, and all electronics fans like us make them regularly. Circuit board is used to electrically connect all the elements according to schematics. So, circuit boards, what are those things? Well, let's start with the fact that we can go even without a board at all. This is called point-to-point construction, so beloved by audiophiles of all kinds. It was used long ago when everything was big and there were no boards. The essence of this method is to use pins of the element themselves, make connections with hard wire or special buses. Point-to-point construction is used even nowadays. It is simple, fast, allows you to assemble devices literally on your knees and is not demanding on skills. However, with the complication of the circuit, the process steadily turns into a torture, and a device starts to look like a meaningless bunch of wires. Here is just a very good example of point-to-point construction, which tells us that the author of this masterpiece has lots of spare time. Another type of board allows you to test your idea instantly and make changes to the circuit literally on the fly. It's called breadboard. Assistant Horseman, please show us how and with what sauce it is used with. The key feature of the breadboard is solderless installation. It opens almost limitless possibilities for prototyping and quick debugging. Such boards can be often found in various projects on Arduino, the main slogan of which is simplicity. Breadboard is usually assembled from sections containing two power buses and two fields of sockets, connected with each other in a linear way. However, the breadboard still remains a platform for experiments. Making finished devices on such boards is not really practical for quite understandable mechanical reasons. The other type of board is breadboard for soldering or just protoboard. It is usually, except for special ones, a matrix of holes with a gap of 2 and 54 mm, tenths of inch, which suits deep mounting. Elements on the protoboard are being installed into holes and soldered. The connections are being created with wires. Unlike solderless breadboard, such a board already allows practical use, especially if you have straight hands with soldering. Board like that can be easily stuffed into a case and called a device. But all of this is unworthy of a self-respecting evil genius. The printed circuit board is made for a specific schematic, and essentially it is a piece of dielectric with conductive traces on top, bottom and sometimes inside. A blank for the board is usually a piece of textilite with copper foil applied to it. In production, of course, the process consists of much larger number of technological operations, but at first approximation it comes down to 4 stages. Apply trace pattern to the copper. Etch the board. Remove excess copper. Drill holes for elements. Apply protective solder mask. But unfortunately, our boards usually look like a craft of a goblin. What about you, fellow handyman? How many times you've been thinking that such a result is unreachable for you while holding a factory-made PCB in your hands? But making a high-quality PCB by yourself is not that difficult at all.
So go ahead, show us.
Well, no. If you do it somehow, you'll get something. Practice is a good thing. But without a theory, it's blind, deaf and drunk. Let's go step by step. The first stage is drawing. There are plenty of ways to do it for each taste and all fingers and thumbs. Actually, you can just draw traces by hand, with nail polish, paint or even a permanent marker. But we shall not pay much attention to this method. It is suitable only for real simple boards with loose mounting and large sizes. And by the way, it looks really ugly, like a craft of a goblin. Toner ironing is much more interesting. I mean, toner transfer method, or TTM. Thousands of boards have been made in this way. It is as easy as pie and accessible to everyone. Let's take a brief look at the technology. We print a mirror pattern of PCB on a laser printer. Print it in bold, forget about toner saving. It is better to do it on special thermal transfer paper, but in harsh reality everything was used. From stickers to those glossy magazines. There is no better use for them after all. Next, we apply our template to well-washed and degreased copper, take the iron and begin to iron with strands of the bear. Let it cool, tear off the paper, swear, fix blanks with a permanent marker, swear again, go start over. Start over again, swear again, and finally get the result. However, despite all its advantages, TTM has serious problems based on the porous structure of toner. And while large polygons can be fixed with a marker, there's nothing you can do with sticky traces. So TTM is limited in resolution, which makes it difficult to use with modern packages, especially with SMD. There is a way to increase accuracy almost to photographic. Actually, the process really looks like old-school photo printing. In a simplified form, the technology looks like this. We have a blank with a layer of photoresistant material applied to it. Then we apply photomask and expose it with ultraviolet light. Then the blank is being developed by washing off unnecessary photoresist. So the board is ready for etching. There are different types of photoresist. It can be liquid or film. The film is glued to the copper like adhesive tape when liquid is applied by spraying. Photoresist also differs in action. It can be negative or positive, so different types of photomasks are used. Seems that there is nothing to add, but nothing stands still. Now the market offers blanks with a photoresist layer already applied. This is much more convenient because it allows you to exclude a whole technological operation from the process. I should mention that photomask is not the only way to expose photoresists. The template can be transferred by projection, for example, or a CNC laser machine can be used. But we will not dwell on such methods due to their low level of availability. Next step is chemical etching, and there are plenty of ways to do it, but how to choose which one is the best and how to compare them. The reaction rate can be evaluated with redox potential, also known as oxidation reduction potential. It measures the tendency of chemical spices to acquire electrons during reaction. Let's start with classics, almost synonymous to the etching process, good old ferric chloride. The method is as old as the world and based on the chemical reaction of water solution of iron 3 chloride with copper. As a result, we obtain iron 2 chloride and copper chloride. Let's calculate redox potential. The difference between normal potentials and driving force for this reaction is 434 millivolts. That's not bad, however, that's not so good. The potential and speed of the reaction gradually decreases while reaction products accumulate in solution. That must have been noticed by everyone. And some people start to do really weird things. They believe that the solution can be raised from the dead by sedimentation of copper from it on iron. Everything is used: nails, bolts, paper clips and other scrap. However, this outputs only a bluish-green liquor, which slowly turns into a good-for-nothing black liquid, which, when disposed, decorates the plumbing in cheerful colors of rust. But if those guys had studied chemistry well, they would have understood that during copper sedimentation solution accumulates only iron 2 chloride, which is completely useless in dissolving copper. The issue of solution regeneration could be resolved by adding hydrochloric acid, but the thing is that if you have it and understand how to use it, you don't need even to think about ferric chloride. Advantages of this method. Suitable etching rate. The solution is easy made by eye. Environment temperature is not so critical. And the main thing, ferric chloride dissolves copper only, so the template could be drawn literally by anything. Disadvantages. Noticeable reduction in etch rate during the process. And for sure the most important minus. Ferric chloride is poorly stored, it's being hydrolyzed and with air access tends to crawl out of any leaky storage, polluting with itself and the products of its hydrolysis all surrounding objects. Well, I'd say ferric chloride is perhaps the worst way to etch a board. All your family will hate you for that. Brown stains will tend to appear everywhere.
Yeah, even on kids' clothes.
It was not me, it was the cat. Let's try something clean. Copper sulfate and salt, for example. In a simplified form, the reaction chain looks like this. First, we got copper 1 chloride and then sodium sulfate. And then comes the reaction of copper chloride and sodium chloride, which produces sodium dichlorocuprate. As we can see from the equations, salt plays a key role, since copper barely doesn't react with copper sulfate. So let's calculate redox potential. The driving force for this reaction is slightly less than with ferric chloride, about 400 mV. Despite that used solution resembles a black liquid, it absorbs oxygen from the air and can be regenerated by acidification with, for example, hydrochloric acid. Advantages. First is availability of copper sulfate, which is widely used in agriculture. Unlike ferric chloride, it doesn't leave stains. Well, it actually leaves stains, but blue, and they could be washed off with a weak acid solution. Disadvantages. Low etching speed. If you, my fellow handyman, didn't know, copper sulfate is quite toxic, may cause vomiting and respiratory burns. Recently, the price of it beats records, while the packaging sizes are systematically decreasing. What's next? Nitric acid? Smoky acid, as they call it. The reaction produces copper 2 nitrate, nitrogen dioxide, also known as brown gas, and water. The reaction is exothermic. Therefore, when solution is spontaneously heated, the reaction accelerates itself. And to tell the truth, the method is so risky that I don't even want to talk about it, and for sure shall not recommend using it. Nitric acid is extremely dangerous itself, and brown gas is deadly poisonous. Is that what you really want? Heat of the season – persulfates. A very interesting and popular topic. One substance, persulfate of sodium or ammonium, in fact, during the reaction decomposes into 3: hydrogen peroxide, sulfuric acid and sulfate, sodium or ammonium, that doesn't react with anything. So we need to constantly heat the solution for its hydrolysis. Let's take a look at the reactions. That produces copper sulfate and sodium or ammonium sulfate. The redox potentials are a little bit more complicated. The driving force of the reaction seems to beat a record of 133 volt. But in practice, such a potential is not achievable, because persulfates, even with strong heating, do not hydrolyze instantly and completely. Advantages. High redox potential and etch rate. Leaves no dirty stains. As well as ferric chloride is one-component solution. Disadvantages. Not that easy to get, unlike ferric chloride. Instead of stains, tends to make holes in pans, which is not that nice. Heating is required for the reaction to proceed. Solutions of high concentrations are used, since more than half of the solution appears to be a ballast sulfate. Not very careful attitude to the photoresist. You gap a little, bald spots appears on the traces. Peroxide and hydrochloric acid. Probably one of the best ways. But first things first. Let's start from the formulas. The reaction goes with formation of copper 2 chloride and water. So redox potential will be like this. It seems from the beginning that redox potential is the same as with persulfate. But hydrogen peroxide is already present at its maximum concentration, which makes it possible to achieve maximum redox potential. Advantages. Excellent speed, literally in front of your eyes. Doesn't leave dirty spots. The process goes rapidly even at room temperature. High availability. Peroxide can be bought in pharmacy, and salted electrolyte is suitable instead of hydrochloric acid. There is only one disadvantage. Use of strong acids in the state of nature leads to holes in pans and, you know. As it turns out, the nature of acid used in conjunction with peroxide is not really important and will only affect the rate of copper etching. That means that you can use any suitable acid that is not oxidized by hydrogen peroxide. For example, you can go to the kitchen and take citric acid or vinegar. Although I shall not recommend using vinegar because the smell is disgusting. Citric acid is available at any store, has sufficient strength and doesn't smell. Moreover, it forms a strong complex with copper which excludes any influence of the reaction products on its rate. To speed up the process, you just add sodium chloride, ordinary salt, that is not consumed at all. The overall reaction looks like this. As a result, we have copper citrate and water. And redox potential 1.77 volt, which is absolute record. Advantages: maximum etching speed, leaves no dirty stains, the process goes rapidly even at room temperature, no hard to find components used, the solution is safe for body and clothes. Disadvantages: copper citrate is slightly soluble and may settle as a settlement on copper's surface. To prevent that, do not have to save citric acid. The solution, however, is less careful to the photoresist and sometimes incidents occur. The next step is application of a solder mask. But let's talk about the mask next time. Looks like I'm really talking too much today. It is time to start doing something. So let's finally try the most accurate method, photoresistive. And now I appeal to all TTM adepts. Guys, leave the past behind. I know, this method was not bad for its time, but it passes. The density is growing while the size of the elements is decreasing. We are moving to SMD, well, it's really better without holes, you know. The future has already come, let's learn to live in it. Yeah, I know everything you want to tell me, that I don't understand anything, that TTM is cool, that I just don't know how to cook it, that your boards are just great, I know. But let's see how many of us switched from TTM to photoresist. Yeah, and how many of us have switched from photoresist to TTM. So let's finally leave the past behind. We will experiment with blend called Kingston, which can be easily found on the internet. They call it textilite, although in effect that's not quite true. It doesn't contain fiberglass, so you can't cut it off with scissors. Somebody immediately rushed to consider this as a disadvantage, but this can be turned into advantage, because what can be cut off can be broken. Let's draw a few boards first. Some of them are pretty simple, but one has high density and minimal gaps. What do you think? Let's get started. We will need a nice cup of tea, you can go ahead without it, a blank that could be already unpacked. However, be careful and do not accidentally light it up. Protective film should be removed only before the exposure, and pay attention to the lighting. The most important detail, a high quality photo mask. Literally everything depends on its quality. A couple of thin glasses, those that used in photo frames will be quite suitable. Just make sure that they let through hard ultraviolet. A metal ruler, fine marker, sharp knife, container for chemicals, a soft brush, optional tweezers, an ultraviolet lamp, and finally several clips to fix glasses. When making a double-sided board, two photo masks are required for the top and bottom layers. They should be combined with each other as accurately as possible and fixed with staplers. The smaller are pads and holes, the more accurately you need to combine the templates in order to avoid problems with drilling. Let's measure the dimensions of our future board. After marking, we take a knife and make cuts. Easy at first, then harder, and then crazy. It is helpful to make small cuts along the edges with a hacksaw. Then we can make cuts on the other side, in the same way increasing the pressure. And finally, well, give me a second. And finally break. And now, dim the lighting just in case and carefully remove the protective film. Put the blank on the glass and apply the photomask. To reduce side expose, print the photomask in a mirror, so the ink side can be against the photoresist. Cover with a second glass and use clips. Before the expose, I strongly recommend to line up the expose time experimentally. It may depend on photoresist type, the power of the lamp and the distance to it. Repeat the process for each board. For single-sided boards, the use of second glass is not so critical, but when it comes to a double-sided one, the second glass saves time, tea and brings harmony. The next steps are development of the photoresist and etching, so it is time to prepare chemicals. My dear left-handed fellow. Left-handed? Did I say so? My fellow handyman, that's what I mean. Always, but always use protective gloves when working with any chemicals of any degree of causticity, even for 5 minutes, even if only moving them to another place. Always use gloves. Otherwise, you are bound to get in trouble. You used to touch a female with those hands, and what will you do with a female without hands? If you know what I mean. To develop a positive acting photoresist, we need 0.7% solution of caustic soda. That means that for 1000 parts of water we need 7 parts of caustic soda. or 1 gram of caustic soda goes into approximately 143 grams of water. We weigh 1 gram. We add water. I always use deionized water. You never know what to expect from the tap water. If you don't have caustic soda, you can try something for pipe cleaning. Just ensure that it's based on sodium hydroxide. Place the boards into container and add the developer. Help yourself with brush, however without enthusiasm, no pressure, otherwise photoresist will be damaged. The double-sided board should be periodically turned over, but make sure that there is no garbage at the bottom of the container. Any grain of sand can ruin everything. Standard proportions of etching solution are 100 grams of pharmacy peroxide, 30 grams of citric acid, and 5 grams of salt. Since the days when I still was messing with ferric chloride, I have been using such a reactor. It consists of 2 containers. The outer one is filled with water, which makes it possible to keep the reaction temperature at the required level, and the second, narrow one, is filled with solution for etching. Such geometry allows you to visually control the process and reduce the consumption of chemicals to a minimum. By the way, it's really convenient to use adhesive tape to fix the boards. As we can see, the reaction goes literally in front of our eyes. Here they are, almost finished boards. Let's put them into water. Next is double-sided one. To wash photoresist out, the same caustic soda is used. We just only need to increase concentration up to 3%. As we can see, that's quite enough. Photoresist dissolves in a few seconds. Boards are etched. We can now ensure about their quality. The next operation is drilling. I use such a simple drilling machine that I made by myself. It has lightning and an automatic power supply that we may discuss someday. Speed control is very important, so we can start with low RPMs to avoid risk of dancing on board surface, and then RPMs can be increased automatically. First, we drill holes with a minimum diameter, then bring them to a desired one for certain elements. We're almost done and deserve to have a nice cup of tea. It remains for us just to lightly sand the boards. That's it. Now we can take a closer look and be proud of ourselves. Thus, we made several boards of various degree of complexity. All operations took us no more than an hour and a half. Do not need any secret knowledge or something. There's no rocket science and this is available to everyone. The next step is applying of a solder mask, but let's talk about the mask next time. How do they say? Put your thumb up, subscribe to the channel and press the bell. And if you find any of this useful, consider supporting the project on Patreon. And yeah, write down in the comments how I did everything wrong and what will you do in my place. That's all, folks. See you next time.